podcast, and we have the illustrious, the overeducated Dr. Logan Graves with us today. He is in optical science land, so we have several optical engineers on Odd Engineer, but he's in the imaging side of optics, and that's anything that has to do with creating an image like a camera or a telescope or a viewfinder or anything like that. He's in that world, which is not my world, so I'm going to learn some stuff too. And when he's not doing that on Odd Engineer, co-founded a couple different companies. One of them is Intuitive Optical Design Lab, where he's done optical engineering work and actually worked with my company, Spirestarter, before. And he's working on another company right now that is PM software for optical projects, and you can find that at eleoptics.com. And on eleoptics.com, there's also an optical engineering, optical science podcast that's specially focused for that. So if you're an optics nerd, totally check that out. I'd love to just go into your background and learn more about how you got into optics world and a little bit more about the medical stuff that you're working on too. But wherever you want to start, just
Sure. I always like talking about the medical and biomedical applications. That was one of my favorite components. So just to start off with how I got into it, I started at the University of Arizona, and like just about every college student, I had no idea what I wanted to do.
Are you from Arizona, by the way?
I am from Arizona. We are kindly called desert rats, or at least that's how we refer to ourselves. I guess it did kind of line up the one pet project, so to speak, that's always really interested me is how could you build, better diagnostic tools for medicine. And when I was a freshman, I started on this research and continued with it for a few years, but I was in a research lab called the Tissue and Spectroscopy Lab. I worked with Dr. Utzinger and Dr. Bhaskar Banerjee, and Timothy Rankowski was a grad student that I was under, and we were looking at how do you identify colon cancer earlier to, prevent colon cancer death. The earlier you catch it, the better. And without getting into too many of the unpleasant details, it's surprisingly hard to image colon cancer with the wavelengths of light, for example. So the work we were specifically doing was, instead of having the patient have to drink, a cocktail that would cause fluorescence.
I know.
And instead of making the patient drink something that makes things glow, you could just possibly use a combination of, of light wavelengths, and things would, but lesions and cancerous tissue would glow anyways. It's fantastic, right? The patient doesn't have to drink anything, and there you go. You have your better imaging for the doctor. So it's not this mysterious, like, I think that's something, it might not be. So that was really fascinating. Another thing that they've done in this area, just very briefly, is you can mechanically accomplish something by just using a balloon in the colon to expand the colon. So instead of having folds like this, right, where you might have cancerous tissue hidden behind a fold, very simply, you put a balloon up, there's no folds, it can't hide anywhere. And to get very advanced, Dr. Bhaskar Banerjee has gone on to form a company called Omniscient Lab. I think it might just be Omniscient, but I have to give this plug because it's one of the coolest things. He worked as well with the professor at the university, Dr. Ron Liang. They made an endoscope that looks backwards. So you don't need a balloon. You just have a creative optical design, and it looks forwards and sideways and backwards, and nothing can hide from you, right? And all of this is great because at the end of the day, what it means is that you catch colon cancer earlier and people have better outcomes. So
very cool.
Sure. So I signed on. Jim Burge at the time was affiliated with what's known as the Large Optics and Fabrication Group, and they were tied in with the people in the basement of the optics building making big mirrors for telescopes as well. So not quite as large as the quote unquote mirror lab, but nonetheless pretty large. Specifically, they're working on the Daniel K. Inouye Solar Telescope, and this is a 4.2 meter diameter telescope. I almost blinked. That'd be really bad because I worked on it for so long. And this telescope's the primary mirror specifically is just mind-blowing. It's made, first of all, it's made out of zero dur, which is a crystalline substrate that just doesn't expand when it heats up.
Zero dur? What is
Zero
it?
dur. Zero dur. They even got the branding name locked down. It expands, but it doesn't expand much. And why that's relevant is that the Daniel K. Inouye Solar Telescope, DKIST for short, is a giant microscope to look at the sun on something called deflectometry, which was a metrology method, just a method to test what is the shape and surface quality of mirrors. And that was what his lab was doing. That was what the research that I got involved with was doing was, okay, we have this DKIST mirror downstairs, let's go test it. Let's come up with new research for how can we quickly test it and how can we test it accurately, repeatably, etc. So that you know the idea. It's a 4.2 meter diameter mirror. It takes forever to test that if you're testing subsections. And anytime that I'm stitching the subsection, there's going to be errors. And this is something we can get into later, but when people use interferometry and try to do subaperture measurements, those little overlaps can cause weird errors. So we use an interferometer. We also use deflectometry. We also used infrared deflectometry, which was new at the time. So we could test it when it was rough and in the grinding state. We could test it. Yeah.
Wow.
We could test it when it was super polished. And nominally, we took it from about 50 microns RMS, or root mean square, down to about 1 micron RMS. And those numbers probably don't mean anything to anyone that, doesn't frequently grind mirrors down, but roughly what it means is that you take it from something that looks totally flat and not reflective at all. So think about like that matte paint that you've seen, or you'll see the custom cars go by with matte paint jobs, right? It looks like that. It's a piece of glass or it's a piece of crystal that looks like not reflective, period. And you polish it down to the stage where you say like, yeah, I can see a reflection. I got something. That's the grinding phase. It can extend beyond that in other cases, but nominally that's the grinding phase. And you enormously cut down on the fabrication time. When I'm in the grinding process, I can go like 1,000 orders of magnitude faster in terms of removing material, getting to the shape I want, as when I'm polishing, right? Because I'm just taking it away. I'm using this thick grit. I'm going down really quick. If I know what I'm doing, this is fantastic, because I can say like, perfect, cut away, chop away, whatever, and bam, you have what you want. If I'm polishing, it's like when you're making a statue. Instead of using your hammer and chisel and you're really just knocking things away, you're now like, okay, I'm using this tiny tool to get just the right shape, which is great, but it's really slow. So if you can test accurately in the infrared for a rough surface, if you have that, you can really shave off time and therefore costs. We've been involved in a large number of spaces. We've worked on LiDAR type applications, building up LiDAR from scratch. That was really interesting. We've worked on things like endoscopes and how do you accomplish kind of the right design for some of these really funny, weird, ultra niche, ultra custom things that have to go in a body and have unique environmental requirement.
If you'd like one-on-one guidance from Dr. Logan Graves, you can book an appointment with him directly on oddengineer.com. Otherwise, for more details and links, check out the full article on SolidSmack.com. Thanks for watching.